Welcome to The Explainer. I'm so thrilled you're joining us today because we're going to unpack something that honestly often feels like magic, but is actually rooted in some truly elegant mathematics, and that's computer vision. Have you ever stopped to wonder how a machine, which, let's face it, essentially just processes ones and zeros, can look at a photograph and actually understand what it's seeing? How does an autonomous car recognize a stop sign, or your phone instantly recognize your face? Well, today we're demystifying that exact process. We're pulling back the curtain on how computers detect features, starting from the most basic corners all the way up to incredibly complex algorithms like SIFT.
Okay, let's quickly map out our journey. We'll hit the basics of machine vision, move on to finding edges and corners, explore the scale invariant revolution, map out the SIFT algorithm, and finally, wrap up with matching features like humans.
Part 1. The Basics of Machine Vision. Let's build our conceptual scaffolding right at the foundation of image processing.
So I want to pose this fundamental question to you. How does a computer actually see an image? I mean, to a machine, a photograph isn't a beautiful landscape or a towering cathedral. It's literally just a giant grid of pixel intensities. It's a sea of numbers. The fundamental challenge here is figuring out how to group and analyze those numbers to find distinctive regions. We need points of interest that are repeatable and distinct, no matter what angle you're looking from.
Look at the stark difference between a flat region, an edge, and a corner. Picture a tiny window sliding over the image. If you move that window in any direction over a flat region, nothing changes, right? The pixels all look exactly the same. If you slide it along an edge, nothing changes along the direction of the edge itself, but it does change if you move perpendicular to it. But a corner is the sweet spot. If you move that tiny window in literally any direction over a corner, you get a massive change in pixel intensity. That huge shift in all directions makes corners incredibly valuable anchor points for a computer.
Section 2. Finding edges and corners. Let's escalate the problem and see how the math actually works. To hunt down those corners, we use the Harris corner detection algorithm, which goes all the way back to 1988. At the heart of this is the structure tensor matrix. Now please, don't let the math intimidate you here. Conceptually, this matrix is just a mathematical way of calculating exactly what we just talked about. It measures the image derivatives, the changes in intensity, along the x and y axes. It's essentially the engine that tells the computer whether that little sliding window is passing over a boring flat spot, a straight edge, or a highly distinctive sharp corner.
So the crucial point is that by combining these specific mathematical steps, we create a really robust detection system. First, the algorithm calculates Sobel gradients to find sharp transitions from dark to light. Then it builds that structure tensor matrix and applies a corner response function to score how corner-like a pixel is. But here's the absolute coolest part: non-maximum suppression. See, the math initially highlights a thick, messy cluster of pixels around a corner. Non-maximum suppression acts like a laser focus, thinning that messy cluster down to one single precise pixel peak. Finally, a threshold just filters out the noise.
And this gives us that incredibly satisfying before and after payoff. We start with a distorted checkerboard, and after applying the gradients, the matrix, and that non-maximum suppression, the algorithm successfully and cleanly isolates the structural anchor points, the exact corners of the squares. It's perfectly invariant to translation and rotation, meaning you can spin that checkerboard all day long and the algorithm will still nail those exact spots.
Section 3. The Scale Invariant Revolution. Because what happens if the object we're looking at gets bigger or smaller?
This brings us to a stark contrast, and honestly a major historical hurdle in computer vision. Think about it. A corner in a small image might just look like a smooth, flat edge if you zoom in close enough. Harris corner detection is fantastic if the object spins or moves sideways, but it completely falls apart when an object changes size. That limitation is exactly what makes the Scale Invariant Feature Transform, or SIFT, such a massive revolutionary breakthrough. SIFT doesn't just survive rotation and movement, it survives scale.
Section 4. Mapping the SIFT algorithm. Let's move over to SIFT and see how it builds a completely robust visual system.
SIFT is just a brilliant piece of engineering, and it relies on a sequence of very critical steps. It starts by systematically blurring the image to create a scale space, calculates the difference of Gaussian, eliminates the bad key points, assigns orientation to handle rotation, and finally, generates a highly distinctive key point descriptor. Let's break down how it pulls that off. The absolute secret sauce for handling zooming in and zooming out is the difference of Gaussian, or dog pyramid. The algorithm takes your original image and creates multiple, progressively blurred versions of it. Then it mathematically subtracts one blurred image from the next. By finding the differences between these blurred versions, we build a multidimensional scale space. The computer looks for points that stand out as maximums or minimums across all these different levels of blur. If a point stands out, whether the image is crisp or heavily blurred, well, you've got yourself an incredibly robust key point that the machine can recognize from literally any distance.
Once SIP finds a good key point and figures out its orientation, it has to describe it so it can be recognized later. And the sheer data depth here is just wild. 128, every single individual key point is ultimately described by a 128-dimensional vector. We aren't just talking x and y coordinates here, we're talking 128 distinct dimensions of data for one single tiny speck on an image.
And here is exactly how we get that massive number. The algorithm takes a 16 by 16 pixel neighborhood around the key point and it divides it into 16 smaller 4x4 subblocks. For every single one of those subblocks, it calculates an 8-bin histogram based on which way the light and dark edges are pointing. So 16 subblocks multiplied by 8 bins, that gives us exactly 128 dimensions. It becomes a highly specific, totally unique signature for that one specific point.
Section 5. Matching features like humans. The hard math is done, but how do we actually match these points across different photos? So we have these unique 128-dimensional fingerprints. But there's a catch. What if the computer gets confused by repeating patterns? Imagine taking a picture of a skyscraper with hundreds of identical windows. To solve this, we use Lowe's ratio test. The system doesn't just find the best match, it finds the best match and the second best match, and then compares them. If the first match and the second match are too similar, specifically if the ratio of their distances is greater than 0.8, the computer basically realizes it's confused and strictly rejects the match to avoid a false positive. It literally forces the computer to do a double take.
And just look at this visually stunning payoff. Two images of the Notre Dame Cathedral, entirely different angles, different lighting, different scales, and yet the SIFT algorithm, using those 128 dimensional descriptors and Lowe's ratio test to filter out the noise, works flawlessly to draw lines connecting the exact same architectural features across both images. All of that intense mathematical scaffolding totally culminates in this perfect matching system.
To summarize our explainer today, this comparison perfectly encapsulates the landscape of feature extraction. Every algorithm is a tool, and you just have to pick the right one for the job. You have Harris, which is incredibly fast but fails at scale. You have SIFT, which is scale invariant and highly accurate, but computationally heavy and slow. And then you have modern alternatives like ORB, which try to give you real-time speed with solid invariance. Knowing the pros and cons of each is exactly what makes you an expert in computer vision. We have literally gone from simple pixel grids to massive arrays of data that allow machines to perceive reality. Every single time you unlock your phone with your face or use an augmented reality filter, millions of calculations are happening in milliseconds to find those corners, build those descriptors, and match those features. Now that you know the mathematical magic behind how machines find and match these 128-dimensional points, how will you look at the visual world differently? Thanks so much for joining me on this explainer, and keep learning.